Hello everyone. Today I will discuss about some properties of moduli in complex analysis. This is lecture 2. Some properties of moduli. Theorem 1. The modulus of the product of two complex numbers is the product of their moduli, that is modulus of z1 into z2 is equal to modulus z1 into modulus z2. Proof. Modulus of z1 into z2 whole square is equal to z1 into z2 into z1 z2 whole bar is equal to z1 into z2 into z1 bar into z2 bar, which is equal to z1 into z2 bar by associative property into z2 into z2 bar, and this is equal to modulus z1 square into modulus z2 square, because z into z bar is equal to modulus z square. So z1 into z1 bar is equal to modulus z1 square, z2 into z2 bar is equal to modulus z2 square. Now modulus z1 into z2 whole square is equal to modulus z1 into modulus z2 whole square implies that modulus of z1 into z2 is equal to modulus z1 into modulus z2, that is modulus of product of two complex numbers is equal to the product of their moduli. Modulus of z1 is equal to modulus of z1 by z2 into z2, which is equal to modulus of z1 by z2 into modulus of z2 by theorem 1, which implies that modulus of z1 by z2 is equal to modulus of z1 by modulus of z2, that is theorem 2. The modulus of the sum of two complex numbers is less than or equal to sum of their moduli, that is modulus of z1 plus z2 is less than or equal to modulus z1 plus modulus z2. Proof. Let z1 is equal to r1 e raised to the power I theta 1 and z2 is equal to r2 e raised to the power I theta 2. Then modulus of z1 is equal to r1, modulus of z2 is equal to r2. Therefore z1 plus z2 is equal to r1 e raised to the power I theta 1 plus r2 into e raised to the power I theta 2, which is equal to r1 cos theta 1 plus I sin theta 1 by formula plus, because e raised to the power I theta 1 is equal to cos theta 1 plus I sin theta 1. So this is equal to r1 cos theta 1 plus I sin theta 1 plus r2 into cos theta 2 plus I sin theta 2 is equal to r1 cos theta 1 plus r2 cos theta 2 plus I times r1 cos theta 1 plus r2 sin theta 2 by separating real and imaginary parts. Therefore modulus of z1 plus z2 is equal to square root of real part plus a square of imaginary part is equal to r1 cos theta 1 plus r2 cos theta 2 whole square plus r1 sin theta 1 plus r2 sin theta 2 whole square, which is equal to square root of r1 square plus r1 square plus r2 square plus twice r1 r2 cos theta 1 minus theta 2, which is less than or equal to r1 square root of r1 square plus r2 square plus twice r1 r2, as cos theta 1 minus theta 2 always less than or equal to 1, which gives modulus z1 plus z2 is less than or equal to r1 plus r2 is equal to modulus z1 plus modulus z2. Therefore, modulus of z1 plus z2 is less than or equal to modulus z1 plus modulus z2. The modulus of the difference of two complex numbers is greater than or equal to difference of their moduli. That is, modulus of z1 minus z2 is greater than or equal to modulus z1 minus modulus of z2. Proof. Let z1 is equal to r1 e raised to the power I theta 1, z2 is equal to r2 e raised to the power I theta 2, then modulus z1 is equal to r1, modulus z2 is equal to r2. Here theta 1 and theta 2 are arguments of z1 and z2 respectively. Now z1 minus z2 is equal to r1 e raised to the power I theta 1 minus r2 e raised to the power I theta 2 is equal to r1 cos theta 1 plus I sin theta 1 minus r2 cos theta 2 plus I sin theta 2 is equal to r1 cos theta 1 minus r2 cos theta 2 plus r1 sin theta 1 minus r2 sin theta 2. Therefore, modulus of z1 minus z2 is equal to square root of r1 cos theta 1 minus r2 cos theta 2 whole square plus r1 sin theta 1 minus r2 sin theta 2 whole square is equal to square root of r1 square plus r2 square minus twice r1 r2 cos theta 1 minus theta 2, which is greater than or equal to square root of r1 square plus r2 square minus twice r1 r2, as minus cos theta 1 minus theta 2 is greater than or equal to minus 1 is equal to r1 minus r2, which is equal to modulus z1 minus modulus z2. Therefore, modulus of z1 minus z2 is greater than or equal to modulus z1 minus modulus of z2. Theorem 4. Modulus of z1 plus z2 is greater than or equal to modulus z1 minus modulus z2. Therefore, modulus z1 plus z2 is equal to square root of r1 cos theta 1 plus r2 cos theta 2 whole square plus r1 sin theta 1 plus r2 sin theta 2 whole square is equal to square root of r1 square plus r2 square plus twice r1 r2 cos theta 1 minus theta 2, which is greater than or equal to square root of r1 square plus r2 square minus twice r1 r2, as cos theta 1 minus theta 2 is greater than or equal to minus 1 is equal to r1 minus r2, which is equal to modulus of z1 minus modulus of z2. Therefore, modulus of z1 plus z2 is greater than or equal to modulus of z1 minus modulus of z2. Theorem 5. Modulus of z1 plus z2 whole square plus modulus of z1 minus z2 whole square is equal to 2 times modulus of z1 square plus modulus of z2 square. Therefore, modulus z1 plus z2 whole square plus modulus z1 minus z2 whole square is equal to r1 cos theta 1 plus r2 cos theta 2 whole square plus r1 sin theta 1 minus r2 sin theta 2 whole square, because z1 plus z2 is equal to this, so its modulus square is equal to real part square and imaginary square of imaginary part. Similarly, modulus z1 minus z2 whole square is equal to this, is equal to r1 square plus r2 square plus 2i's r1 r2 cos theta 1 minus theta 2 plus r1 square plus r2 square minus 2i's r1 r2 cos theta 1 minus theta 2. This term and this term vanishes, is equal to 2 times r1 square plus r2 square is equal to 2i's modulus z1 square plus modulus z2 square. Therefore, modulus z1 plus z2 whole square plus z1 modulus z1 minus z2 whole square is equal to 2 times modulus z1 square plus modulus z2 square. Theorem 6. Equation of a straight line. Find the equation of a straight line joining the points z1 and z2 in the complex plane. To determine the equation of the line AB joining the points A z1 and B z2, consider a point PZ on it, where PZ lying on this line segment. Evidently, argument of z minus z1 by z1 minus z2 is equal to either 0 or pi. So, z minus z1 by z1 minus z2 is purely real. Therefore, z minus z1 by z1 minus z2 is equal to z minus z1 by z1 minus z2 whole bar is equal to z bar minus z1 bar by z1 bar minus z2 bar. Therefore, this quantity implies that z minus z1 into z1 bar minus z2 bar is equal to z1 minus z2 into z bar minus z1 bar. After simplification implies that z into z1 bar minus z2 bar minus z bar into z1 minus z2 bar plus z1 into z2 bar minus z1 bar into z2 bar is equal to 0. This is the equation number 1, and this equation 1 is the required equation of the line. General equation of a straight line. We know that z into z1 bar minus z2 bar minus z bar into z1 minus z2 plus z1 z2 bar minus z1 bar into z2 is equal to 0. This is the equation number 1. Multiplying equation number 1 by I, we have I times z into z1 bar minus z2 bar minus I times z bar into z1 minus z2 plus I into z1 z2 bar minus z1 bar z2 is equal to 0. This is equation number 2. Now let minus I z1 minus z2 is equal to A. Then its conjugate A bar is equal to a whole bar of this quantity, and this is equal to I times z1 bar minus z2 bar. Also, z1 into z2 bar whole bar is equal to z1 bar dot z2. Therefore, z1 z2 bar minus z1 bar z2 is purely imaginary number. Therefore, I times z1 z2 bar minus z1 bar z2 is equal to purely real is equal to C, suppose. So, equation number 2 becomes this, if we take this minus I z1 minus z2 is equal to, then this becomes a z bar and this is a bar z and this is equal to c. So equation 2 becomes a bar z plus a z bar plus c is equal to 0, where c is real. This is general equation of a straight line. Theorem 7. Equation of a circle. Show that the equation of a circle in the organ plane can be put in the form z into z bar plus b z bar plus b bar z plus c is equal to 0, where c is real and b is complex constant. Proof. Let a be a complex coordinate of the center C and R be the radius of the circle. So here this is a circle whose center is C at A and its radius is R, and P is an arbitrary point on the circle. Consider any point PZ on the circle. The length of the line CP is equal to radius of the circle is equal to R. Therefore, modulus Z minus A is equal to R. Therefore, distance between the center and the point P is R. Squaring both sides, we have modulus Z minus A whole square is equal to R square, implies that Z minus A into Z minus A whole bar is equal to R square, implies Z minus A into Z bar minus A bar is equal to R square, implies that Z into Z bar minus A bar Z minus A Z bar plus A bar is equal to R square, which implies that Z into Z bar minus A bar Z minus A Z bar plus modulus A square minus R square is equal to 0, as A into A bar is equal to modulus of A square. Taking minus A is equal to B and modulus A square minus R square is equal to C is equal to real number, then Z into Z bar plus B Z bar plus B bar Z plus C is equal to 0, where C is real and B is a complex constant. Inverse points with respect to a circle. 2 points A, Z is equal to A and B, Z equal to B are said to be inverse points of a circle with center O at Z is equal to Z naught and radius R if the points O, A, B are collinear and OA into OB is equal to R square. So that A minus Z naught, so that modulus of A minus Z naught into modulus of B minus Z naught is equal to R square. Then argument of A minus Z naught is equal to argument of B minus Z naught is equal to minus of argument B minus Z naught bar, implies that argument of Z minus Z naught plus argument of B minus Z naught whole bar is equal to 0, implies that A minus Z naught into B minus Z naught whole bar is real and equal to R square. Hence, A minus Z naught into B minus Z naught whole bar is equal to R square is the required equation. Deductions. If Z0 is equal to 0, then A and B are inverse points if A into B bar is equal to R square, that is A into conjugate of B is equal to R square. Therefore, Z1, Z2 are inverse points of the circle modulus Z is equal to R if Z1 into Z2 bar is equal to R square. Thank you very much for watching this video. Please don't forget to subscribe my channel. Please like, share and comment. Please press the bell icon to get notifications.